Good. Shall we get started? Okay, cool. So my name is Kaiming, and I will be joining this random university next month, actually. So today I'm doing an unpaid job. And now let's see what's the title of my unpaid job. Well, it's learning deep representations. And I will talk about it in the context of image recognition and perhaps in some other scenarios. And here is an overview of this tutorial. First, I will talk about what is representation learning and why representation learning is an important problem. And then I will talk about how can we build and train very deep neural networks. And I will talk about a few milestone and influential neural network architectures. Then I will also cover some important components and elements for us to train very deep neural network architectures, including some initialization methods, normalization methods, and the introduction of residual connections. And then I will also cover the applications for image recognition and some sequence processing problems. So first of all, why deep learning? Why, about 10 years ago, suddenly people started to talk about deep learning almost everywhere? So in a nutshell, deep learning is representation learning. And actually, interestingly, more than 10 years ago, deep learning was not popular and was not favored by the mainstream conference in computer vision or in machine learning. And at that time, some of the pioneers in deep learning and neural network architectures, such as Yann LeCun and Yoshua Bengio, decided to start another conference that is more friendly and more open-minded to deep learning research. And interestingly, these pioneers in deep learning decided to name their new conference as the International Conference on Learning Representations. And this reflects how closely related it is between deep learning and representation learning. Then why representation learning is important? Representation learning is a common problem that can be shared across many applications in many areas. A common goal of representation learning is to transform the raw data into some high-level representation space. And we will have better compression or abstraction or conceptualization in the representation space. And when the computer algorithms are operated on that representation space, they can solve very complex problems way more easily. And depending on the scenarios, the raw data can be in many different forms in practice. For example, in computer vision, the raw data could be pixels in images or in videos. In natural language processing, the raw data can be letters or words. In some other scenarios, such as speech recognition or audio recognition, the raw data can be audio waves or spectrograms. And in the case of game playing, the raw data can be the states of the game board. And in some scientific problems, the raw data can be the molecule sequences, DNA sequences, or some other structures. A common problem in many of these applications is on how can we represent the data in some high-level abstraction space such that the computer algorithms can solve the problem way more easily. Now let's take the game of Go as an example. Using computers to solve the game of Go has been believed as a very challenging or maybe even infeasible problem over the last several decades. So part of the reason is that there is an exponentially large number of different states in the game of Go. For example, the board has 19 columns and 19 rows. And if we put everything together, then there would be 361 positions. And every single position may have 3 choices, black, white, and blank. Then this will give us 3 to the power of 361 different states. And this is a huge number. And if the computer algorithm is going to do analysis or maybe even enumeration or memorization in this state space, then it would just be infeasible for today's computer to address this problem using this representation. However, if that is the case, then perhaps we will never solve computer vision or image recognition problems. Now let's think of a very simple case in computer vision. Let's say we will have a very small image, let's say 500 pixels by 500 pixels. And every single pixel may have 3 color channels, red, green, and blue. And every single color channel may have 256 different values. And if we put everything together, then we will have 256 to the power of 3 by 500 by 500 different states, just for a very small image. And if our computer vision algorithm is directly operated on this raw pixel space, and if the algorithm is going to either enumerate or memorize this state space, then we will never solve the computer vision algorithm because this problem is even more intractable than the problem of Go playing. However, this is not how computer vision algorithms address the image recognition problem. Instead of directly working on the raw pixel space, we will use a model to transform the raw pixels into some representations. And today, usually the most successful model for us to do this is to use a deep neural network, such as a convolutional neural network. And then these representations will give us some very good compressions, abstractions, or conceptualizations. And when using these representations, the computer algorithms can solve many different problems, such as image classification, object detection, or image segmentation. Then analogously, going back to the problem of Go playing, we can just think of the board in the Go playing as a very small image. And this image just has 19 by 19 pixels, and every single pixel has only 3 possible colors, black, white, and blank. And then we can use the same idea. For example, we can use a convolutional neural network to process the states of the game and obtain some high-level abstractions. And the computer algorithm can directly work on this high-level abstraction space to do some analysis or do some search. And this will make the problem of Go playing way more easily to be solved. And this is actually one of the many fundamental ideas behind the famous AlphaGo algorithm. This figure is from the AlphaGo 0 paper. And in this figure, the authors compared 4 different versions of the AlphaGo player. And these versions are compared in terms of the ELO rating. And usually a higher rating means a better Go playing performance. And this figure simply shows that by increasing the depth from, for example, 12 layers to 40 layers, we can easily enjoy a huge boost in terms of the Go playing performance. And actually, if we keep increasing the depth of the neural networks, for example, to 80 layers, we're going to see another huge boost in terms of the Go playing performance. And it is interesting to note that this performance is way better than even the best human players in the world. And the AlphaGo algorithm can achieve this performance without using any human knowledge. And it is also worth noticing that for the 4 or 5 different players compared here, many of the other components are exactly the same. So for example, the usage of the reinforcement learning algorithm and the Monte Carlo tree search algorithms are exactly the same. It is only the neural network architectures that are used to learn the representations for Go playing are different across these 5 different versions. So I hope this will give you some sense about how important representation learning is for us to address very challenging problems. Now let's go back to the problem of computer vision. And next I'm going to talk about how can we represent an image in computer vision before deep learning got popular. Let's say we are given an image and we can just view it as a bunch of pixels, and we can directly send this bunch of pixels into a classifier. The classifier can be an SVM classifier, support vector machine, or it can be a decision tree, or it can be a random forest. Usually this is not a good solution because even a small change in the object will lead to a large change in the raw pixel representation space. Then in order to have a better question?
Representation, and if I asked a really good Go player how they thought about the game, and how they represented it, I'd get one thing, I suspect. And if we looked at the so-called representation that the Go system learned, would they look anything like one another? Has anybody done that experiment?
Yeah, that's a very good question. So I'm not a good Go player, but I got to know that there are very fancy terminology about Go playing. The terminology about the expert players sensation about how the current state is. So the Go player has their own internal representations for Go playing. And those internal representations may not be well aligned with what the representations can be learned by computer algorithms. And actually, after the AlphaGo was developed, I believe many of the expert players use the AI to help them to improve their own internal representation of human beings. Okay, good. Okay, let's go back to our story. So in order to have a slightly better representation, we may want to compute the edges on top of the pixels, because this will give us some more robust representations in case the illumination or the colors of the input space may change. Then, again, in order to have yet another better representation, we may want to compute the orientations of the edges, or the histograms of the orientations, or we may run some clustering algorithms on top of the histograms. So actually, this pipeline works pretty well if the problem is simple enough. However, in this pipeline, it requires human beings, or it requires computer vision experts to define what are good representations or what are good features for them to solve the problems on hand. So while the feature designing problem is relatively doable for some low-level representations, such as the definition of edges or textures or colors, this problem would be extremely difficult if we want to define some high-level representations. For example, it turns out to be extremely difficult for us to define, for example, what is a fish, what is a cat, or on the other hand, what is a tree or what is a human. And actually, in computer vision, over the last several decades, defining high-level abstractions and representations has been a major bottleneck in the computer vision community. Deep learning provides another methodology for us to address the computer vision, image recognition, and many other complex problems. A key idea of deep learning is to compose a simple set of general modules into highly complex functions for us to solve highly complex problems. So if there is only one message that you can take away from my talk today, then this is the message. I'm going to repeat it many times in the following part of this talk. So with the help of a general set of modules, it is easy for us to build multiple levels of abstractions and to learn multiple levels of representations. And the concrete instantiations of these modules, such as the parameters or the weight of these modules, can be learned by backpropagation. So the reliance on human knowledge is largely reduced. And again, the learning is done on some larger scale data, so the requirement of human knowledge has been transferred or shifted from engineering the features to another problem of collecting the data that is related to the problem. And overall, all of these key ideas or key concepts of deep learning can help us to greatly reduce the domain knowledge for us to solve the problem on hand. So these are many reasons why deep learning can be a general toolbox for us to solve many problems in many areas. And next, I'm going to talk about how can we learn the deep representations for image recognition, and I'm going to go through a few milestone and influential steps in the history of convolutional neural network development. I will start with the LeNet architecture that was developed about 30 years ago. The LeNet architecture is one of the successful instantiation of convolutional neural networks, or in short, a ConvNet or CNN. Simply speaking, a convolutional neural network is a translation invariant architecture. So by translation invariance, we usually mean if we have some operations inside a sliding window, and when the window is translated by a few pixels, we will still have more or less the same operations. And translation invariance can also mean if we translate the entire input image by a few pixels, we can still have the same output class label if we are doing the classification problem. Then the LeNet architecture has introduced several foundational elements for convolutional neural networks. These elements include the usage of convolutional layers, pooling layers, fully connected layers, and more importantly, the idea of training the entire architecture end-to-end by backpropagation. And again, a convolutional neural network is just one instantiation of the deep learning methodology, which is to compose simple modules into highly complex functions. And next, I'm going to introduce two of these simple modules that are foundational. The first module is the convolutional layer. Simply speaking, a convolutional layer is just local connection plus spatial weight sharing. In contrast to a convolutional layer, one of the most popular layer type is the fully connected layer. In that case, every single output neuron is connected to every single input neuron in that layer. And here, every connection represents a weight or a parameter that can be trained. That is to say, if we have many input neurons and if we also have many output neurons, then we will have a great number of trainable parameters. And that is not ideal. And in order to partially address this problem, people have developed another layer type, which is called a locally connected layer. In that case, every single output neuron is connected to just a small subset of the input neurons, and usually in practice, these small subsets will just be in a sliding window or a local neighborhood around the output neuron. And the introduction of a locally connected layer can greatly reduce the numbers of trainable parameters. And a convolutional layer is just one step ahead. That is to say, when we slide the window in different positions of the input image space, we can share the weight across different spatial positions. So let's zoom out a little bit. Again, the convolutional layer is local connections plus weight sharing. And we are going to see that these two concepts, local connection and weight sharing, are everywhere in neural network design. Another important component, another important module in convolutional neural network is a pooling layer. The role of a pooling layer is to reduce the size of the feature map so it can greatly reduce the computation required if the input image is big. On the other hand, a pooling layer can also help to achieve local invariance. That is to say, if our input contents undergo some local jittering inside a small window, we will still able to obtain more or less the same representations in that window. And this can help us to get more abstraction representations, and this is a desired property for us to do classification problems. Then, given this simple set of general modules, next I'm going to walk through the learning architecture step by step. Even though this architecture has been proposed by more than 30 years, it is always enjoyable and inspiring for us to walk through this classical architecture. In this case, the input to the neural network has only one color channel because it is grayscale. And in this example, the spatial size would be 32 by 32. Then it will perform the first set of convolutional kernels, which has a spatial size of 5 by 5. And in this case, it has 6 different output channels. And this will give us the first set of output feature map. And in this case, the spatial size is 28 by 28. And because our convolutional layer has 6 output channels, then this set of feature maps will also have 6 output channels. Then we can apply the first pooling operation to reduce the spatial size by a factor of 2 across each dimension. Then we will arrive at the next set of spatial feature map, which has a spatial size of 14 by 14. Then we are ready to apply the next set of convolutional layers, again, which has a kernel size of 5 by 5, and at this time, it has 16 different output channels. Then we will arrive at the next set of feature map, which has a spatial size of 10 by 10 here, and again, the next pooling layer to reduce the spatial size, and we will arrive at the final set of spatial feature map, which has a spatial size of 5 by 5. And after that, we can just flatten this feature map, and we will process it with the first set of fully connected layers, and the second set, and the output fully connected layer, which has 10 channels, in this case, for a 10-class classification problem. And at the high level, the entire architecture is very simple. It is just a composition of several basic modules, which is just convolutional layers, pooling layers, and fully connected layer in this case. The learning architecture actually works extremely well if we have the data to train it. Unfortunately, this architecture has been ignored for more than 20 years after it was proposed. Part of the reason is that we don't have the compute or we don't have the data to fully demonstrate the power of this architecture. At that time, the largest data set, surprisingly, it was the largest data set at that time, was the MNIST data set, which has 50,000 images in 10 classes. This data set is good enough to train a very small model, but it's not enough to fully convince the computer vision community to adopt convolutional neural networks in their problems. Then the real revolution of deep learning happened in 2012, and it was introduced by this AlexNet paper. In my understanding, there is only one thesis in this AlexNet paper, which is to scale up convolutional neural networks. And the scaling up involves actually several aspects. The first aspect is about the data. The AlexNet was trained on the ImageNet dataset, which has 1 million images and 1,000 classes. And actually, at that time, it is way more bigger than many of the other datasets that people have been studying. And actually, at that time, it's far beyond people's imagination that we can train a neural network architecture end-to-end on raw pixels in such a large-scale dataset. On the other hand, the AlexNet architecture is actually big. And in the abstract of that paper, the authors specifically said this is a huge architecture, and this architecture has more than 60 million parameters and over 600,000 neurons. This model size is actually also way more bigger than many of the other models on those days. Then in order to train such a large model, even with the help of a large scale data, people need to introduce effective techniques to reduce overfitting. And the AlexNet paper explored two very effective techniques in this regard. One is data augmentation, and the other is dropout. These two techniques are still widely used in today's neural network training technologies. And another aspect about the AlexNet paper is about its excellent engineering work. It has explored the potential of using GPUs to train their models. And actually, they have paved the foundations for GPU training for the next 10 years. They have introduced two basic concepts about GPU training. One is data distribution, and the other is model distribution. In the case of data distribution, different samples in the same mini batch can be handled by different GPUs, so the computation per GPU can be largely reduced. Then in the case of model distribution, different sets of filters or different layers can be stored in different GPUs, so it can also help to largely reduce the memory consumption. And these are still the foundations in today's GPU implementation. And here is just a side-by-side comparison between the original LeNet architecture and the AlexNet architecture. At the high level, they are just the same thing because they are just a composition of many simple and general modules, convolutional layers, pooling layers, and fully connected layers. They are just the same thing. Then what would be the difference? So why is AlexNet revolutionary? The first difference is that the AlexNet is deeper. It has 3 more convolutional layers and 1 more pooling layer. And these layers can help it to learn higher level abstractions from larger scale data. Then it is going to have a stronger representational power than the shallower models. Then another difference is the usage of the ReLU activation, as you have seen in Philip's talk. In the original LeNet, the activation function is a sigmoid. And when the input signal is too big or the input signal is too small, we will have 0 gradients and when using the sigmoid activation function. And as a comparison, in the AlexNet, for the first time, it started to explore the usage of ReLU activation function to train a very deep neural network architecture. And in the case of ReLU, it is only when the input signal is smaller than 0, it will have 0 gradient. Then when you have many activation functions in a very deep neural network architecture, you will have a much higher chance of having non-zero gradients in the backward propagation process. And it turns out that this can largely facilitate the training of very deep models. So in some sense, the introduction of the ReLU activation is kind of a revolution of the deep learning. And another huge difference between these two architectures that has been largely ignored by many people is that the AlexNet is actually a wider architecture than the original LearnNet. And in the terminology of deep learning, by wider, we usually mean the model has more channels. Then, by having more channels for every single layer, we are going to have a richer set of features, then it will be more representative than a narrower model. The success of the AlexNet in the ImageNet dataset has drawn a lot of attention in the community of computer vision. And in the next year after the AlexNet was proposed, the computer vision community started to pay more attention into the understanding of the neural network behaviors. And one way for the computer vision community to obtain better understanding is by visualization. And a very successful visualization method is to answer the following question. So what input can produce a specific feature? In order to answer this question, we can do the following two steps. First, we just need to set a feature map as a one-hot vector or a one-hot tensor. So that is to say, for this specific feature map, there is only one element that is non-zero, and all other elements would be set as 0. Then we can use exactly the same backpropagation algorithm to propagate this one-hot feature map from the feature space back to the pixel space. Then we will have some visualizations about this feature on the pixel space. And next, I'm going to show some visualization obtained in this way. And I'm going to show the visualization of a convolutional neural network that has 5 convolutional layers. And here are the visualization of the first convolutional layer. Here, I'm going to show the features on the left, and I'm also going to show some stimuli on the right. So by stimuli, I mean these are the patches or input images that will have the strongest activations in the corresponding features. And as we can see in the first layer of this neural network, they are usually kind of edge detectors or some color detectors. And this behavior is very similar to a classical image recognition system in which the first layer is an edge detector. And here are some visualizations of the second convolutional layer in the same network. And in this case, we can see that the features are slightly higher level than the features in the first layer. And we can see some of the features show some patterns of textures, and in some other cases, they show some local shapes, such as a circle or a corner or the shape of a thin line. And this is why we say these features may be higher level than the features in the first layer, which are just edges. Then here are the visualization of the third layer. In this case, we start to see that it begins to show some semantic patterns. For example, for this feature, it starts to show some semantic patterns about the upper body of human beings. And in another case, it starts to show the patterns of something like a net or a honeycomb. Then again, here are the visualization of the fourth layer. And again, it is higher level than the representations of the previous layer. And there are some shapes of dog heads or perhaps the shapes of the body of a bird with 2 legs. And again, these are the visualizations of the last convolutional network, the convolutional layer in this network. And again, this would be higher level. It is not perfect. For example, in this layer, it will mix several things together. But in some other examples, for example, for this filter, it will give the representations for different types of dogs. And for this filter, it will give the representations for different types of animals with eyes. And actually, in computer vision, these high-level abstractions or high-level representations are very difficult to be designed by hand. So these high-level representations are exactly what the computer vision community have been looking for over the last several decades. So this visualization helps to convince the computer vision community that deep learning or deep convolutional neural networks are the right way to go. And as a byproduct of this visualization, at that time, the computer vision community started to make a very significant discovery. At that time, they discovered that these deep representations are transferable. And in my opinion, this is actually the single most important discovery in the deep learning revolution. Then what does it mean by transferable, or what does it mean by transfer learning? In my opinion, transfer learning is just an amazing idea. Let's say if we can train a larger scale network on a larger scale data set, and if we can discover that this network will learn some high-level representations or high-level abstractions, then we can hope this high-level representation is not just related to this data set. These high-level representations can also be used in many other smaller scale data sets that have something to do with this larger scale data set. That in order to enjoy this benefit, we can transfer these features to some smaller scale data set, and usually we can do this transfer learning by fine-tuning. For example, we can just train a small part of the neural network. And this can be done on just small scale data sets. And this discovery can enable deep learning models to be applied on small scale data sets. So you don't need a large scale data set for your specific task to train very large scale models. You just need a small amount of data set that is relevant to your task. Then this discovery completely revolutionized the computer vision community, because with the help of transfer learning, we can enjoy the benefits of deep learning in basically all small-scale data sets, and they can achieve unprecedented accuracy in many of the computer vision tasks. So this is just game-changing. So in this sense, some of the larger scale data sets, such as the ImageNet data set, is no longer a fine-grained or a tedious fine-grained classification problem that has more than 1 million images or 1,000 classes that I'm not going to tell. The ImageNet dataset becomes the engine for us to learn general representations that can help basically all computer vision tasks. And this discovery of transfer learning is so influential that its impact is far beyond just computer vision. For example, the GPT or the ChatGPT model was also developed in exactly the same principle. Then next, I'm going to talk about another work that is kind of my favorite. This work is called VGG, which is short for Visual Geometric Group, which is a group at the Oxford University. It can also be short for a very good group, something like that. The VGG architecture is very simple. It is just the idea about how can we build a very deep neural network architecture without bells and whistles. So the VGG network is a highly modularized design, and it only has convolution layers, pooling layers, and fully connected layers. And all the convolution layers are actually 3 by 3, so you don't need to carefully design these layers. So the VGG network just simply stack the same type of modules, and they can build very deep neural network architectures, for example, up to 90 layers, which are twice as deep as the previous deepest model. And interestingly, for the first time, they show clear evidence that a deeper model would be better than their shallower counterpart. So this seems to be a surprising statement because, well, actually, at that time, there was very little clear evidence that a deeper model is better. A part of the reason is that before the VGGNet paper, when people increase the depth of the neural networks, they also do something else at the same time. So there was no clear evidence that going deeper is the only reason, is the main reason for the network to get better accuracy. Then in the VGGNet paper, the authors have designed very carefully controlled experiments. They try to remove all the bells and whistles in the architectural design. They introduce very little config engineering, and they develop very simple rules for them to set the number of channels or the number of layers for every single stage. And all the thing they do is just to add more and more 3x3 convolutional layers. This is a very simple design. This is extremely elegant. However, these simple baselines are very hard to beat. Actually, in those years, the VGG networks are just the state-of-the-art architecture in computer vision. It is the default backbone architecture for us to solve many different problems, including classification, detection, and segmentation. And they can easily outperform the counterparts that use shallower neural network architectures. Actually, the VGG network are just the state-of-the-art before deeper neural network came along. Then there is just one caveat about the VGG network architectures. That is, these models were not trained end-to-end. Surprisingly, these models were trained by a technique that is called a stage-wise training. For example, in order to train a deeper neural network architecture, they need to pre-train a shallower counterpart of it. Then they add, for example, 2 more layers on top of the previous model, and then they keep fine-tuning it. So this stage-wise training strategy is actually not ideal. It is actually against the end-to-end training philosophy of deep learning. In order to train these model architectures from scratch, we need to develop better initialization algorithms. Then, in the next year after the VGG network paper, the community started to pay more attention into the network initialization issue. Then, now let's zoom out a little bit again, and we are going to talk about why are these deeper neural networks are more difficult to train. Intuitively, a very deep neural network will have just have a stack of many building blocks and many modules. Now, let's say if every single building block will do something wrong or it will introduce some troubles, then after we stack this building block for many times, then our troubles will just simply be accumulated. So in practice, we are going to see some exploding signal problem, or we may also see some vanishing signal problem. And in this case, we may need some network initializations to help us to get the neural networks to start training. Next, I'm going to delve a little bit deeper into the network initialization algorithms. Here I show a simple layer, which is linear in a neural network. In this case, the input X would have X nodes or X neurons, and the output Y will have M nodes, and the output is just a linear transform of the input, and the transformation will be represented by a weight matrix W. It's the simplest thing in a neural network architecture. Then if we assume all the elements here, for example, X, Y, and W, are independent with each other, and if we further assume there is only linear activation inside the entire neural network, then we can show that after the signal being processed by one layer, the variance of the signals will be scaled by a scaling factor. For example, this equation basically says the variance of the output of this layer equals to the number of input neurons times the variance of the weight matrix times the variance of the input signal. So this layer will scale the signal, will scale the variance of the signal by this scaling factor. And we can apply this formulation many times in a very deep neural network if we don't have any activation, or if our activation function is linear. We are going to see that the variance is still scaled by the product of many scaling factors. This equation basically says the variance of the network output equals to the product of these many numbers times the variance of the network input. And this is the formulation of the forward propagation. And we can do some math, and then we will get the backward formulation, and the backward formulation is in a very similar fashion. And basically, this equation says if you want to compute the gradient of a shallow layer by backpropagation, then the variance of this gradient will equal to the product of these many scaling factors times the variance of the gradients of the network output. So this is the backward propagation formulation. Then basically the product of these many factors basically says if the scaling factor for every single layer is smaller than 1, then after this effect to be accumulated by many layers, you are going to experience the vanishing gradient problem. That is to say, your network is not going to train. It seems to be saturated or it seems to be converged. But the real reason is that it just does not receive enough gradient for it to train. On the other hand, if this scaling factor is greater than 1 for every single layer, you are going to experience the exploding gradient problem. That is to say, your network will be diverged, perhaps in the first iteration. Then in order for the network to at least start training, we need to develop good initialization algorithms. And the previous derivation will lead us to this initialization method, which is known as the Xavier initialization in the PyTorch or TensorFlow packages. Basically, you want to set this scaling factor as 1 for every single layer. And you may either want to set the forward formulation as 1 or the backward formulation is 1. This is how you can initialize the weight in your neural network for every single layer. And usually in practice, you just need to set one or the other form, and it doesn't really matter that much. And this network initialization can help us to preserve the variance of the signals throughout the process, throughout the propagation of the signals. And the previous derivation was based on the assumption that the activation function is linear. And in practice, usually that's not what you want. You may want to introduce a ReLU activation. Then we can also show that with the introduction of ReLU, you may want to have a slight change in this formulation. And that is to say, you need to add this factor of 1/2 in these equations. Intuitively speaking, the ReLU activation may cut half of your signal in the training process. That's why you need to introduce this scaling factor of 1/2. And even though this seems to be a very small change comparing with the previous version, it turns out to be very important. That is because if you are going to introduce some problem or some trouble for every single layer, then after many layers, if you don't do things right, you are going to experience the vanishing gradient problem in this case. And these initialization methods can help us to train the VGG network from scratch without the requirement of stage-wise training. And this is about how we can appropriately initialize the network architectures. Then let's go back to the year of 2014. And next, I'm going to talk about another very interesting work, and that is in parallel with the VGG network. And this line of research is usually referred to as GoogleNet or GoogleNet or Inception. A common thesis of this research is about how can we design deep and at the same time economical convolutional neural networks. There are several interesting ideas involved. The first idea is to use multiple branches. For example, you may have 1x1, 3x3, or 5x5 convolutions in the same module. And at the same time, you may use a 1x1 convolution as a bottleneck. That is to say, you can use this 1x1 convolution to flexibly control the number of channels in your neural network. You may either decrease the number of channels or increase the number of channels in some other cases. Also, as a byproduct, the GoogleNet has also introduced a 1x1 convolution as a shortcut in their module. So it is a shortcut because this 1x1 convolution can be shallower than the other branches in the same module. So it can be called a shortcut. Well, actually, in my opinion, the Inception architectures are just crazy, and there are millions of versions of different designs. Most of the times, if you are lucky enough, it's good. It will give you a very compelling compute and accuracy trade-off in terms of neural network design. However, it also introduced another problem. So the crazy design of these architectures may break the simple assumptions that are required for us to develop the initialization algorithms. So you may either want to develop some other initialization algorithm specifically for all this crazy design, or you may want to introduce some other modules that can help you to train these neural network architectures. And motivated by these Inception architectures, people started to look at another family of methods which is called normalization modules in the neural networks. And in 2015, people started to look at normalization modules. Actually, long before that, people had realized that if we want to train a very good neural network, if we want the neural network to start converge, you may want to normalize the input. And actually, even today, this is what you need to do as a preprocessing for your data. And on the other hand, the network initialization method we have just talked about can also be considered as a form of normalization. This is because we want to keep the variance of the signals more or less unchanged during the process of signal propagation. And this normalization for network initialization are based on some analytical derivations or analytical assumptions. And this assumption are only valid at the beginning of training, and they will be broken during the process of training. And this is not ideal. In order to address this problem, people want to develop another module which is basically a layer inside the neural network. And these modules will perform normalization throughout the process of training. So they can keep the signal being normalized throughout the process. And if you want to apply these modules for all layers, they can also help you to keep the signal normalized for all layers that you specified. And also, these normalization modules can be trained end-to-end by backpropagation. So they are just yet another simple and generic modules in the toolbox of deep learning methodology. And here is an example of the typical computations that can be performed by a normalization module. And usually there would be 3 steps that's involved. In the first step, we may want to compute the expectation or the variance of the input signal to this module. And then we can normalize the input by subtracting the mean and dividing by the standard deviation. And this operation may reduce the degree of freedom because we do this normalization. So we may want to compensate for this reduction by introducing another linear transformation, which can simply be ax plus b. And these 3 operations can be put into a single layer, which is a normalization module or a normalization layer. And this layer conceptually can be used basically everywhere or anywhere in the neural network architectures. In practice, there are many types of normalization modules, and one of the difference between these modules is about the support set in which they compute the mean and variance. For example, in this case, I show a tensor of a 2D image. Here, the n is the axis of the batch size, and c is the number of channels, and h and w is the height or width, which is the spatial size. And this operation represents the batch normalization operation. Basically, it will compute the statistics across the spatial domain and also across the batch domain. This is why it is called a batch normalization. Then there are also many other types of normalization layers. They only differed in the definition of the support sets. And today, one of the most popular choice for us to use, or perhaps the default choice for us to use, is the layer normalization operation. It is also worth noticing that its definition in ConvNet or in transformers can be slightly different. Then, why are these normalization modules important? So first of all, the usage of these modules can enable the models to start training. Otherwise, they will just stop training or they will just diverge at the very beginning. On the other hand, even when the models can start training, the introduction of normalization modules can help to speed up the convergence, and it can also help to improve the accuracy when the model converge. Then next, I'm going to talk about ResNet. And before that, let's zoom out a little bit and let's record what is the key idea of deep learning. So the key idea is to compose a simple set of general modules into highly complex functions. So in order to compose a large number of simple modules, we may want to build a deeper neural network architecture. And this is the foundation, and this is also the basic motivation behind the ResNet architectures. So in this work of residual learning, we demonstrated that deep learning or deep neural network architectures can get way deeper than people might have imagined. And also, interestingly and surprisingly, this can be done by a very simple component, which is just an identity shortcut. And conceptually, basically, it does almost nothing. However, the introduction of this simple component can enable neural networks with hundreds of layers to train from scratch and to achieve better accuracy. And next, I'm going to tell a little bit about the ResNet story. The ResNet was motivated by an empirical observation, which is known as the degradation problem. We have discussed very good initialization methods and also very effective normalization modules. Then, with the help of those modules, it is sufficient for us to train very deep neural network architectures from scratch and obtain some accuracy. Then, as such, is deep learning just as simple as stacking more and more layers? Unfortunately, the answer is negative. In practice, it turns out that the models will degrade very quickly after 20 layers. And this degradation is not because of overfitting. So that is to say, the deeper models not only has worse validation accuracy, they will also have worse training accuracy in practice. So it turns out that these deeper neural networks are just more difficult to train. And this is counterintuitive. Now let's have a thought experiment. The deeper models actually have a richer solution space than the shallower models. So that is to say, the deeper neural networks should not have a lower training accuracy. It is easy for us to have a solution to the deeper neural network by construction. We can simply train a shallower neural network to achieve some good accuracy if we can do that. Then we can just copy the trained layers from this shallower model to the corresponding layers in a deeper counterpart. Then for the other layers that are unique to the deeper layer, we can just simply set them as identity mappings. And the presence of this solution to the deeper neural network architecture suggests that it should at least have the same training accuracy as some of the shallower counterparts. So the empirical observation of degradation suggests that the optimization may not be able to find this solution, or the optimization may not be able to find a solution that's similar enough to this one. And this motivates us to develop a framework which is called deep residual learning. And again, here, let's zoom out a bit and let's think of a very deep neural network architecture, and then let's focus on a small subnet inside a very deep neural network architecture. And in this illustration, this small subnet has only 2 layers in this case. And then we use a function hx to denote the underlying desired function that is to be fit by this small subnet. Then in the case of a classical vanilla neural network, the only thing we can do is that we hope these 2 layers can fit this underlying function of hx. Then the idea of residual learning is different. We don't need to use these weight layers to directly fit this function hx. Instead, we may want them to fit another function, which is fx, and this function will represent the delta or the change that we can make on top of the input to this small subnet. And in order to have the original desired function, we just need to add the fx into the inputs of this subnet. And this addition can be easily achieved as an identity mapping, which connects the input of this subnet to the output of this subnet, and the signal will be merged by element-wise addition. And this will also turn this subnet into a residual block. And in this residual block, the weight layers will perform a function which is called a residual function. Basically, the residual function is just the incremental changes on top of the input. And now let's think of the entire residual block as a function that we want to use. If the identity mapping is optimal for this function, then it should be easy for us to achieve it because we can set all the weight layers as 0. And if identity mapping is almost optimal, then we may also be able to have a good solution because we can set the weight as some small numbers. And in this sense, actually, the idea of residual learning encourages a building block to make small and conservative and incremental changes. However, by putting many small changes together, it is still possible for us to have to learn a very complex function. And this also follows the deep learning methodology. And again, as a byproduct of the introduction of the residual block, it is easy for us to have another initialization method. We can just set the weight as some small numbers or set them as 0 at the beginning of training. This is to say, the entire residual block will just be identity mapping or similar to an identity mapping at the beginning of training. So the signal in the forward process and also in the backward process can be easily propagated with this identity mapping at the beginning of training. So you don't need to worry too much about the initialization algorithm. Then it is easy for us to adopt this idea to build a very deep neural network architecture. So in some sense, you may just need to add this many identity connections into a vanilla neural network, then you can turn it into a residual neural net. Or equivalently, this can be thought of as simply stacking many residual blocks to create a very deep model. So in this sense, the introduction or the design of a residual block actually becomes the new generic design or the new generic modules for us to build very deep neural network architectures. So after the introduction of ResNet, people started to focus on the design of every single building blocks. And perhaps one of the most successful design is the transformer block. And then after that, you just need to stack the same type of block for many times, and you don't need to carefully design every single specific layers when you have many more layers. And then here are just some results about ResNet. In this figure, the x-axis is the depth of neural network, and the y-axis is the classification accuracy. And this figure basically says a vanilla neural network will start to degrade very quickly after 20 layers, for example, and the ResNet can keep improving after many layers. And the same pattern can happen on ImageNet and many other data sets, and this pattern can be summarized in this form. So without the help of residual connections, the neural network will start to degrade after a certain point, depending on your scenarios. And with the help of residual connections, it can keep improving and when you add more and more layers. And this is a highly desired property. Then here is a checklist of the several things that you may do to build and train the very deep neural network architectures. And many of these concepts are just about how we can have a healthy signal propagation in the training process. And this aspect include the usage of a ReLU activation or other activations of a similar shape, and also the usage of an appropriate initialization algorithm. And it also include the introduction of normalization modules and residual connections into your neural network architectures. Good, I have talked about learning deep representations with convolutional neural networks for 2D images. The next, I will also briefly talk about how can we learn deep representations from 1D sequences. A classical model for us to do 1D sequence modeling is recurrent neural networks, or in short, RNN. A recurrent neural network is a very special kind of neural network which has loops in its connections. So that is to say, given a recurrent neural network unit, it will take the input from the current time step, let's say xt, and then it will produce a hidden state given that input, for example, ht. And this hidden state will be used to determine the output at that time step, and this hidden state will also be used as the input to the next time step. And if we unfold this recurrent neural network architecture along the time axis, we can see that it is actually yet another weight sharing model with the weight shared across the temporal dimension. So, and also, this architecture is also a locally connected formulation. For example, for every single unit, it is only connected to the input of this time step, and it is also connected to the immediate previous time step. So again, we see that weight sharing and local connections are still two of the key properties in a recurrent neural network design. And this is conceptually very similar to a convolutional neural network. Then how can we build a deep recurrent neural network? And it also turns out to be very simple. In some sense, you just need to view the state from a recurrent neural network unit as a new sequence, and then you can process this sequence by using another unit. So that is to say, you can just stack many recurrent neural network units together, and you will have a deeper neural network. For example, here I show the case of a 3-layer recurrent neural network. And in this case, if we consider the output of this neuron, it will depend on the output of all the shallower layers. And it will also depend on all the previous time steps in the same layer. And this is just a property of recurrent neural network architectures. And here is an example of deep recurrent neural networks in practice. This example is from Google's neural machine translation system that was developed for their product in 2016. And in this case, they stack several LSTM units to make this deep recurrent neural network. And LSTM is just a special form, but very effective form of RNNs. In this work, the author reported that in order to build this very deep LSTM model, they still need to use the residual connections. They report that with the help of residual connections, they can train a deep LSTM with up to 16 layers and enjoy the benefits of going deeper. And if they don't use the residual connections, they observe the degradation problem just after 4 layers. So interestingly, this observation is very similar to the observation we made on convolutional neural networks. And again, this demonstrates the power and the generality of the deep learning methodology. That is to say, if we develop a very effective and very general component from one application, then it is likely that you are going to enjoy the benefit in some other applications. So in this case, the original residual connection was developed in the scenario of convolutional neural network for 2D image processing. But its behavior can also be observed in a completely different scenario with recurrent neural networks for 1D sequence modeling. Then, recurrent neural network is not the only way for us to model 1D sequences. We can still use the classical convolutional neural network to achieve more or less the same goal. We just need to apply a sliding window across the 1D dimension, and then we can perform a convolution on the 1D sequences. And if we want to have some causal reasoning, we may want to make a small change here, which is we may want to make the convolution to perform some causal computation. That is to say, for the kernel, for the convolutional kernel, it can only see the current time step or any of the previous time step. It is not going to see any of the future time steps. Then in the case of a convolutional neural network, the limitation is very obvious. That is to say, if you want to capture a longer context, you need to build a deeper neural network architecture. This is because for every single layer, the context length will be limited by the kernel size. For example, in this case, for this neuron, its context only depends on the current time step and the immediate previous time step. So in order to have a longer context, for example, in this case, you may want to have more layers. And this neuron will depend on up to 3 time steps away. And this is how you can have a longer context when we use convolutional neural networks for sequence modeling. And next, I'm going to discuss yet another concrete example. This example is from DeepMind's WaveNet architecture, and the application here is for audio generation. In this case, they not only use the causal convolution, but they also generalize it with another operation which is called a dilation. So a dilated convolution means the convolutional kernel does not need to depend on the immediate previous step. It can depend on a time step that can be many time steps away. Then the dilation operation can help us to greatly increase the size of the convolutional kernel, and it can help us to capture longer context. But even so, the authors still need to stack many convolutional layers to build a very deep convolutional neural network to capture long context. And as such, they still need the help from the residual connections for them to enjoy the benefits of training deeper neural networks. And here is a summary of different sequence modeling paradigms conceptually. In the case of a recurrent neural network, for every single layer and for every single time step, it can see the full context. That is to say, if we consider this neuron, its computation will depend on the computations of all the previous time steps in the same layer. And this could be a desired property if you want some long-range reasoning in your application. However, on the other hand, also because of this property, the computation of recurrent neural network is not feed-forward. That is to say, in order to compute the outputs of this neuron, you need to wait the outputs of all the previous neurons to be finished. So this behavior is not friendly to parallel implementation in GPUs. So in practice, the recurrent neural networks are not efficient in GPU implementation. As a comparison, the convolutional neural network had completely different behavior. On one hand, the model is fully feed-forward. So for every single neuron in the same layer, you don't need to wait for the other neurons to finish their computation. So this is very friendly to parallel implementation in GPUs. So usually the convolutional neural networks are very efficient in GPU implementation. But on the other hand, as we have discussed, the context length would be limited by the size of the convolutional kernels. And this is not a desired property. Then how can we enjoy the best of the both worlds? And this is why the attentional mechanism has been introduced. Simply speaking, in the attentional mechanism, we allowed every single neuron or every single time step to see every single other time step in the sequence. So as such, for every single neuron, it will be able to see the full context from the previous layer. So if modeling a long-range reasoning is what you want, then this is a desired property in the neural network architectures. On the other hand, in the attentional mechanism, all computations are feed-forward. So you don't need to wait. You don't need to wait the computation of the previous time step at the same layer to finish. So this feed-forward computation is also very friendly to GPU implementation. The attentional mechanism is a core idea behind the very popular architecture which is known as the transformers. Because time is limited, I'm not going to delve into the technical details of the transformers, but I'm going to share some of the intriguing properties of the transformers design. The first property is that in the transformers, we allow every single node to see every single other node as what we have discussed. And another interesting property, which to the surprise of many practitioners, is that actually the attention computation is parameter-free. So you don't need to introduce any parameters. That is to say, if you are given 3 sequences, let's say QKV, which is short for queries, keys, and values, then the attention computation does not need to introduce any trainable parameters. So this is unlike a classical fully connected layer where every single connection may represent a trainable parameter. In the case of the attentional computation, in this attentional computation, every single connection represents no trainable parameter. It just means these two things are related to each other. So if the attentional computation is parameter-free, then where are the parameters? So interestingly, in the transformer architecture, all the parameter layers are feed-forward. The parameter layers will be used for us to obtain the sequences that are called QKV, and they will also be used in the MLP blocks that is to transform these sequences in the representation space. And in some sense, all these parameter layers are just kind of one-by-one convolutional layers. And again, all these layers are locally connected because they are only connected to the current time step. And all these layers have weight sharing across the time dimension. And again, we can see that local connection and weight sharing are still the two key properties in neural network architectures. And also, the transformer architecture is a very deep model, so we need to rely on a certain type of normalization operations and also the residual connections for us to train these very deep models. There are many successful applications of the transformer architectures, and perhaps the most popular and most famous one is the generative pre-trained transformers, or in short, GPT. Simply speaking, the GPT model is a representation learning model for natural language processing. The GPT models are designed for a task which is known as next word prediction. In this task, the model is given a prefix of a sentence, and it is asked to predict what would be the next word after this prefix. In this case, the sentence could be, for example, the students open their something, and the model is asked to predict something, and with some probability, the models may say book. And this model, the GPT model, is trained on a large scale data set collected from the internet. So it is able to learn very good representations about the natural languages. It is also going to learn the knowledge that is contained in this language data. And the GPT model is the foundation behind many of the language applications, including ChatGPT. And actually, in order to enjoy the benefit, we still need to rely on the transfer learning paradigm. That is to say, we pre-train this model on larger scale data, then we need to fine-tune or transfer this model in some smaller scale data sets. Another successful application of transformers is the AlphaFold application. And simply speaking, AlphaFold is a representation learning method for the application of protein folding. In this case, the input to the neural network architecture is amino acid sequences, and the output of the architecture are just the protein structures. And this architecture has 48 transformer blocks, and the architecture would be trained on a larger scale protein structure dataset that has been collected by human experiments over the last several decades. And interestingly, even though many of these components, such as the transformer block or the usage of residual connections, were originally developed for many other applications, such as natural language processing or image recognition, this exact same set of building blocks can be applied to a completely different problem of protein folding. And again, this demonstrates the generality of the deep learning methodology. If you develop a very effective set of tools, then you may be able to enjoy the benefits of these tools, perhaps in completely different areas. Then we are ready to go back to computer vision, and we're going to introduce another very successful work, which is called the Vision Transformer, or VIT. So conceptually, VIT is just the application of transformers to 2D image processing. And it turns out that the idea can be very simple. We just need to prepare an input image as a sequence of non-overlapping patches. Then we can apply the transformer architecture on this 1D sequence as if it is whatever any other 1D sequences. And it turns out that this simple idea is very successful and very effective, and today it is one of the default choice for us to do image recognition in computer vision. And the significance of the VIT architecture is not just within computer vision, because for the first time, it demonstrated that the transformer architecture can be a unified architecture for many problems, including natural language processing, computer vision, or audio recognition, or 3D processing, and many other sequence processing problems. And again, it demonstrates the generality of the deep learning methodology. Now here is a conclusion of this tutorial, and this would be some takeaways from this part. And in this tutorial, I have introduced what is representation learning and why it is an important problem. Representation learning can be a common problem and that we may have across different areas and for different applications. And deep learning and deep neural networks address very effective tools for us to address the representation learning problem. And again, the key idea of deep learning is to compose a simple set of generic modules into highly complex functions. And the deep learning idea can provide us general tools to address different problems in different areas. And I hope you will be able to use these tools in your areas in the future. And that's it for this part.